So now we're going to look at derivatives of exponential functions. And today we're going to focus on y equals base e to the exponent of x. So let's estimate the limit as x goes to infinity of 1 plus 1 over n raised to the exponent of n. We're just going to use our calculators to evaluate this limit. So let's start with 10. So if n equals 10, that means I'm evaluating the... If n equals 10, then we have 1 plus 1 over 10 raised to the exponent 10. And if you evaluate that using your calculator, you get approximately 2.59374. I'd like you to try bigger and bigger numbers for n until the number is accurate to 5 decimal places. So take a moment now, use your calculator, see how far you need to go, and I'll include a table here in just a moment. And you notice from my table I had to get up to an n value of 1,000,000 and 10 million in order to get a number accurate to 5 decimal places. So what is this number? This irrational number is called Euler's number, and it's represented by the symbol e. Similar to pi, e is an irrational number. However, e is defined by the following limit. The limit as n goes to infinity of 1 plus 1 over n to the exponent of n. And as we've just discovered, the number lies somewhere between 2.71 and 2.72. Before we look at the derivative of the exponential function with a base of e, let's first practice using your calculator to evaluate expressions with Euler's number. So first of all, let's start with e cubed. So on your calculator, you're going to have to find a lowercase e, possibly with an exponent attached to it. And if you type it in correctly, if you want to evaluate e cubed, you should get approximately 20.086. So please try that now and make sure that you found the correct button on your calculator and that you know how to use it. For the second one, 2 times the square root of e, you should get approximately 3.297. And for a final one, 1 divided by e squared minus 5, you should end up with negative 4.865. And if they don't work, let me know and we'll try to figure out what button you need to use and how you need to use it. Alright, example 2. What if we want to solve exponentials involving Euler's number? So let's solve e to the exponent x equals 5. So our first step is to isolate for x by using logarithms. So we want the log base e of the number 5. And if your calculator has Euler's number attached to it, then it also has what's called the natural logarithm. And on your calculator, it might look like an in, but it's actually ln. So log base e is the same thing as ln. And on your calculator, if you type in the natural logarithm and the number 5, you should get approximately 1.609. If you want to check that this is correct, I can take e to the exponent of 1.609, and you see you get approximately 4.998, which is close to 5. If I want to solve e to the exponent 2x equals 32, I have 2x equals the log base e of 32. So 2x equals the natural logarithm of 32, and therefore x equals ln 32 divided by 2. Using your calculator, you should get approximately 1.733. And our final one, c. So first of all, I'd minus 8 from both sides. So I get e to the exponent of 1 minus x is equal to 9. Then I'd get 1 minus x is equal to the natural logarithm, or the ln of 9. So negative x equals ln of 9 minus 1. And therefore x equals 1 minus the natural logarithm of 9. Using your calculator, you should get that x is approximately equal to negative 1.197. Why are we even bothering to discuss this irrational number e? And here is why. Let's take a look at its derivative. So we want to find the derivative of y equals e to the x. We're going to use first principles and see what happens. So we get the limit as h approaches 0 of e to the x plus h minus e to the x all over h. We can rewrite the power e to the exponent of x plus h as e to the x, e to the h. And notice now we have a common factor of e to the x in our expression. So let's take that out. So we have the limit as h goes to 0 of e to the x times e to the h minus 1 all over h. This term here has no h attached to it, so we can actually move it to the front of our limit. So this is the same thing as e to the x times the limit as h goes to 0 of e to the h minus 1 over h. But we still need to evaluate this limit here. Notice if I sub in 0 right now, I get 0 over 0. If we get 0 over 0, remember that's our indeterminate form, and that means there's possibly a value for this limit. So how can we determine this value? Well, there's no real shortcut to get us there, so what we're going to do is use a table of values. So I'm going to try to determine the limit as h approaches 0 from the left. So 0 from the left could be negative 0.1, negative 0.01, and negative 0.001. And then I'm also going to test the limit as h approaches 0 from the right. And we're going to see if they equal the same number. So take a moment now, using your calculators, evaluate the limit as h approaches 0 from the left and the limit as h approaches 0 from the right. So when I tried this, I ended up with 0.9516, 0.9950, and 0.9995. So we can see as h approaches 0 from the left, the limit appears to be approaching 1. Now let's check the right side. So notice the limit as h approaches 0 from the left of e to the h minus 1 over h, it equals the limit as h approaches 0 from the right of e to the h minus 1 over h. So therefore the limit as h approaches 0 for e to the h minus 1 over h equals 1, since the left and right hand limits both approach a value of 1. So if we take this number now, we know that that limit equals 1. We're going to take this number, we're going to replace that limit by the value of 1. So what we end up is with the following, that the derivative of e to the x is equal to e to the x times 1, or is just equal to e to the x. So what we just shown is that the derivative of e to the x is e to the x, that the derivative is the exact same thing as the function. Probably the easiest shortcut to remember. The function and its derivative are the same thing. Alright, so now that we know that shortcut, let's look at some more complex derivatives involving Euler's number. So determine the derivative of y equals e to the exponent of 3x. So we can see we have a composition of functions. So we have the outer function f is e to the x, and we have the inner function g is 3 times x. So let's take their derivative. So f prime is e to the x, and g prime is equal to 3. Using our chain rule, if we have a function h of x is equal to f follows g of x, then its derivative, h prime of x, is f prime g of x times g prime of x. So what we have is dy over dx is equal to, the derivative of the outer function is e to the x, but then we need to sub in g of x wherever we see an x, and in this case g of x is 3x, so notice we get back the same thing, then times it by g prime of x, so times it by 3. So this derivative is equal to 3 times e to the 3x. Alright, let's go to the next one. The next one is a function times a function, so we're going to need to use the product rule. So g prime of x, remember it's p prime q, so p prime would be 2x times q, which would be e to the x, then plus pq prime, that would be x squared, and the derivative of e to the exponent of x is e to the exponent of x. This one we can even take a step further and factor. We have x e to the x as a common factor in both terms. I take out an x, an e to the x, and an e to the x. And I'm left with 2 plus x. Again, see, we have a composition of functions. So we have the outer function f is e to the x, and the inner function g is x squared minus x. So the derivative of e to the x is e to the x, and the derivative of g prime, is 2x minus 1. So f prime of x will be equal to e to the x squared minus x, so that's f prime g of x, times g prime, which is 2x minus 1. So this gives us 2x minus 1 e to the exponent of x squared minus x. And we're done. D, this is h prime of x, is equal to 3 times whatever the derivative of e to the x squared is. And e to the x squared, its derivative is e to the x squared times the derivative of the inside, which is 2x. So this is equal to 6x e to the x squared. Final one. Notice we have a quotient, p over q. So we need to use our quotient rule. So dy dx is equal to, well, e to the x squared is e to the x squared times the inside, 2x. So that's your p prime, times q, which is x squared, then minus p, e to the x squared, times q prime, which is 2x, over x squared all squared. We can simplify this a bit. This gives me 2x cubed e to the x squared minus 2x e to the x squared all over x to the fourth. And this one I would also simplify. So I can factor out the e to the x squared. I can factor out a 2. I can factor out an x. If I take out the 2x e to the x squared, I'm left with an x squared minus 1 all over x to the exponent of 4. And there's one more thing I can cancel, the x here and the x here. And this gives me that the derivative for this function is 2e raised to the exponent of x squared times x squared minus 1 all over x cubed. And now we are done. All right, final example. Determine the values of x at which the tangent is horizontal. So first of all, we need to determine the derivative for this function. And this is the same as example 3c. It's the derivative of the outside, which is e to the x squared minus x, times the derivative of the inside, which is 2x minus 1. We're going to let f prime of x equal 0. And when we do that, we get 2x minus 1 times e to the x squared minus x equals 0. So now we just need to solve for each factor. So the first one, that's x equals 1/2. 2x minus 1 equals 0 when x equals 1/2. And what about this one? We have e to the x squared minus x equals 0. When does that happen? Well, let's first look at a graph of an exponential function. So for an exponential function, the graph looks something like this, where the range of this graph, y, has to be greater than 0. And if that's the case, e to the x squared minus x can never equal 0. If you tried to solve this using logarithms, you'd end up still with the same problem. You'd end up with x squared minus x equals the natural logarithm of 0. And if you type the natural logarithm of 0 into your calculator, you would get an error. That's because a logarithmic function is the inverse of an exponential, and in that case, the x values have to be greater than 0, and notice we have an x value of 0, so we still can't solve this equation. So we only have one point where the slope of the tangent is equal to 0. Alright, so let's summarize what we just learned. We learned that if you have the function e of x, then its derivative is e of x. If you have the composition of e to the g of x, then this derivative is e to the g of x. Then we're going to multiply by the derivative of the inside, and that would be g prime of x. So please complete the worksheet. That'll help you get more comfortable with using Euler's number, and then try the following questions from your textbook. And again, good luck.